In this video, I'm going to discuss weight and weightless again. Let's see. So let me see. Okay. We said the gravitation, universal law of gravitation is Fg, universal gravitational constant, 6.67 times 10 to the minus 11, m of the object, m. On the surface of the Earth, this is the mass of the Earth, and then divided by the radius of the Earth square. And this is only the case on the surface of the Earth. So you have an object that's m, and I can rewrite this. I can rewrite this like this. Put the mass, and then g m Earth divided by the radius of the Earth square. And this is the little g. And this little g is 9.8 meter per second square, again, on the surface of the Earth. Right? So what would happen? How about at the higher location? If you go up higher above Earth, what happens to this little g? Then g, if the height is going to be significant enough, then it's going to be m, the mass of the Earth, and that divided by the radius of the Earth plus the height above the ground square. So here's the Earth, right? And we have a radius of the Earth. Radius of the Earth. Oh, here. Radius of the Earth. That's about RE. And then you go up high enough that it's no longer, it becomes significant, H. Then a total distance from here to here, D. This D is RE plus H. So that becomes D squared, right? Then let's see, ground. So here's the chart. On the ground, that means that height above the ground is 0 meter. And the little g, which is in meter per second square, we know that's 9.83 meter per second square. When you have a mass that's 70 kilogram mass, then mg, when you have that's about 154 pounds, all right? When you have a 70 kilogram, that's about 154 pounds. And your mg is 688 Newton, all right? What happens if you go to Mount Whitney? A person who has the 70 kilogram weighs 154 pounds. So the Mount Whitney is about 4,500 meter above the ground. And your gravitational acceleration at the top of Mount Whitney, your gravitational acceleration is in fact 9.82. How much does your weight changes? From 688 Newton to 687 Newton. Is that worth going up to Mount Whitney? How about airplane? Airplane flies above the ground, 10,000 meter above the ground. Your gravitational acceleration, see, you can see here, right? Because of the denominator is squared, it does become less. It becomes less but it's not too much, 9.80 meter per second square. That's because, you see, this h, little h, is insignificant. The radius of the Earth, remember? The radius of the Earth is is 6.365 times 10 to the 6 meter. So compared to that, 10,000 isn't much. And therefore, in an airplane, maybe you have a 2 Newton less. As also you can notice that, I hope you notice, is this 70 kilogram. That does not change, right? Does not change with the height. Mass doesn't change with the height. But pounds, Newton should decrease as height increases. But height has to increase significant to the radius of the Earth. And the airplane actually flies above us, isn't that much high compared to the radius of the Earth. And let's see, now we're gonna look into a space shuttle. That orbits around the Earth for 300,000 above the ground. Unfortunately, gravitational acceleration is 8.90. You're still going to have 623 Newton. Not that low. Not that low, right? The communication, so the International Space Station, same thing, International Space Station. H is similar, 36,000 kilometer. Right, and then you have a 9.53. No, sorry, 400 kilometer. You still have in at the International Space Station, calculation is not the same, but 667. You still have a 667 Newton. Let's see. So what does that mean, right? You still have in a space shuttle, you go up in the space and you still have a gravitational, what is it? Gravitational acceleration is 8.9. you're still going to have a 70-kilogram person that has the gravitational force 623 Newton. All right, 623 Newton. Let's see this video. Okay, so this is Crew 1. The SpaceX launch was a few weeks ago on the weekend. The SpaceX launched the Crew 1. And here's the countdown to launch. It's just a minute away from the
Noguchi said the vehicle is alive. Coming up in 10 seconds, we'll look to hear that Dragon is in countdown and Falcon 9 is in startup.
Sorry about that.
Dragon to countdown.
At the start counting down.
Startup and it's now controlling.
50 seconds now until liftoff. That FTS you heard is flight termination.
Dragon, SpaceX, go for launch.
Sorry about that.
SpaceX, this is Resilient. Roger, go.
Go for launch, and at 37 seconds, the International Space Station flying over Kennedy Space Center.
All for one, Crew 1 for all.
Crew Dragon poised to go catch it. 20 seconds till liftoff.
T-minus 15 seconds. Falcon 9 is configured for flight. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition.
And resilience rises. Not even gravity contains humanity when we explore as one for all.
M1E propulsion is nominal.
That's the word we want to hear. Stage 1 propulsion is nominal.
So it's going above.
Seconds into
Here.
this historic mission, flying crew on board Dragon and Falcon 9.
Here, I want you to see the altitude.
Stage 1 is preparing
It's going
to
up
down.
and going up and going up and going up, right?
In preparation
Altitude.
for max Q, which is maximum aerodynamic pressure.
Stage 1, throttle down.
There's that call out for throttle down.
Okay, anyway, it's gonna go up
We're going to
and
shed
go up.
about 70% of the velocity of
196.
that dropping first stage by the time this landing burn completes.
It's around here.
This view inside Mission Control Hawthorne. Teams continuing to monitor the vehicle. Now
So they
traveling
had to
almost
lift off. They're in
27,000
space now.
kilometers an hour.
We see nominal service section Draco checkouts and the
Where
unifier
are they
activation.
loading here?
First trip to space for Victor Glover.
Acquisition of signal, Newfoundland.
So they're in
That
space.
call out
And
acquisition
then
of
I have
signal in
something to
Newfoundland.
show,
That means the
another one to
Newfoundland ground
show.
station is now
Alright.
receiving telemetry from.
And let me see. Where? So let's see. This is at the SpaceX Crew 1. It's in orbit before docking with the space station, but they're already up in above the atmosphere and they're in orbit. And you see,
Inside the cabin, we have our 4 astronauts.
5, actually. We've got Baby Yoda on board trying to take a seat right now, I guess.
I know, I think that's Victor Glover's seat. So
you see what's happening to Baby Yoda?
Maybe Baby Yoda's trying to pilot the vehicle. But some pretty cool views. The crew members are hanging out, quite literally, as they coast to the International Space Station.
Yeah, and as you can see, they're not in their spacesuits anymore. They are in this coast phase, and so they are in their comfortable clothes.
So you see that I hope you see is what you see here is that Baby Yoda astronauts that's in orbit, when it's 300,000 meters above the ground, where you still have if the 70-kilogram person on Earth weighs 688 Newton, you're going to have still 623 Newton at that location. And you see is weightless. They're floating, but you have a significant gravitational force. Why? So what we saw was that above so high, still you're going to have a significant gravitational force because the radius of Earth is so much larger that it's not as big deal. And we also have seen diagram that if you go the run radius above the Earth, you're going to have a significant gravitational force. The gravitational force drops down to 1/4 by the one radius above. That's 6.365 times 10 to the 6 meter above the Earth. You're going to still have 1/4 of the gravitational force. But you know that in space station, in Crew 1, Dragon, Baby Yoda, astronauts, they're all floating. They're all weightless. Why is that? So Baby Yoda. Floating in space shuttle. That means that Baby Yoda astronauts, they're all in weightless. Weightless means not that. Weightless means not Fg equals 0. It means normal force is 0. It's in free fall. Right? So when I throw a ball, let's say I throw a ball like this. If you ignore the air resistance, the only force applied on the ball is gravitational force. This projectile motion. It's in free fall if you ignore the air resistance. Let's see, this is the Earth. This is the Earth. And I'm throwing the ball. So I'm going to throw it, right? It's going to hit the ground. Maybe I throw it harder. So my initial speed will be a little bit bigger. So it goes a little bit farther. It's going to hit the ground. I'm throwing it with a harder. So the curvature of the Earth is when you move 8,000 meter horizontal direction, there is a drop of 5 meter drop. If your initial speed is 8 kilometers per second, that's about 18,000 miles per hour. So if you throw an object that's So you throw harder and harder and harder. At one point, it's gonna match the curvature. It's gonna match the curvature of the Earth. Okay, if you throw 8 kilometers per second, then it can match the curvature that it can keep going around. So this is called orbit. You use that, you have a gravitational force. Gravitational force is constantly there. Fg, right? So you can keep falling. But because it matched the Earth curvature, it goes fast enough, you can keep falling. So what we have seen in a space shuttle, even a space station, satellites, they're in orbit. They keep falling. They're in orbit. They're in free fall. In free fall, you have a normal force to be 0 and it's weightless. So it doesn't mean that zero G, you do have this gravitational force. In fact, you use this gravitational force so you can keep falling. You have a significant gravitational force. Significant gravitational force. Keep falling. Let's see. So here, let's say I can set that. So there's a 2 space shuttle, 2 rockets here. I can set different kind of initial speed. So let's do initial speed like 5 kilometers per second, right? Remember, 5 kilometers per second. And if I fire, one of them, you use the same initial speed to go vertical, and this is to be horizontal. Right, it's not large enough that it hits the ground, right? Maybe I'll increase to 6 kilometers per second. Not large enough. Let's do 7. Almost. And remember, 8 kilometers per second. When you throw it with the 8 kilometers per second, you match the curvature of the Earth, and you see this rocket, it's gonna keep falling. Keep falling. And once it's keep falling, it's constantly in free fall. Free fall means normal force equals 0, so you're in weightless. You have a significant gravitational force. In fact, you use this gravitational force that you can orbit around. Therefore, you can constantly keep falling, and you're in weightlessness. Okay. let's see. I'm gonna show you the OK Go video. To be in free fall. So here is another video that I want to show. It's doing things.
It's Black Friday now, only at Target. This week.
So you see, so when they're in free fall, they're weightless. So what you're going to see is this music video is that this artist, they're going to be in an airplane, and this airplane is going to be in free fall. So let's see. What you're about to see is real, it says. See, when they say this zero gravity, it's not true. It's not true. It's not zero gravity. They're in free fall, all right? Wrong, incorrect. Let's see.
They're not doing what you said. Don't know where your mind is, baby, but you're better off without it. Inside down and upside out, and you can feel it. Don't stop, can't stop until you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. So when you met the new you, were you scared? Were you cold? Were you kind? Yeah, when you met the new you, did someone die inside? Don't stop, can't stop, it's like a freight train. Don't stop, can't stop until you feel it going down. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind is, baby, but you're better off without it. Looks like it's time to decide. Are you here? Are you now? Is this it? All of those selves that you tried, wasn't one of them good enough? Cause you're upside down and inside out, and you can feel it. Inside down and upside out, and you can feel it, feel it. Don't stop, can't stop, it's like a freight train. Don't stop, can't stop till you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down.
Okay, so you see that, let me escape. So there's no wires. Again, there's no wires, there's no green screen. It's just they're in free fall. How can they be in free fall? They're in what's called NASA's Vomit airplane. because you go up and down with the strong. So you got to go. So here's the airplane, right? Flies like this, I guess. Looks a little weird, but that's okay. Tail. So airplane goes up. You're going to go with the strong velocity upward. Then at one point, you shut off the engine. If you shut off the engine, it's going to be in free fall. So starting from here, you go up, inertia takes it, come back down until whatever the distance you can take it. In this period, it's in free fall. And that's about 27 seconds that they can be in free fall of weightless. So I read that they shot 8 consecutive weightless period. They slew down to about 30% in recording so you can match the choreography. And then when they're not in free fall, then they're sitting still to match all that movements. So that's what they did. So it's in free fall. You don't need to be up in a space. As long as you're in free fall, your weightlessness. When the space shuttle, space station, those astronauts are floating, it's not because there's no gravitational force. It's because what is zero? That's right. Normal force is zero, not the gravitational force. All right. So this is the end of the chapter 9, and I'll see you in the discussion.